Hi everyone, my name is Jonas and I work at Apple on debugging technologies. And for the past few months I've been working on adding reproducers to LLDB, the topic of today's talk. So as is the case in any complex software project, bugs are inevitable and LLDB is no exception. And just like we need to compile the compiler, we also need to debug the debugger. So here's a simple example of something that might go wrong. We create a target and we set a breakpoint on line 12 of main.cpp, and then we execute and we execute two expressions. So one to import a module named foo, and then a second one to print bar. But alas, we cannot materialize our variable. So if we're lucky, somebody will file this bug, and the interaction might go something like this. Bob is a diligent engineer, and he files a bug about the materialization issue. And then Alice is an LLDB developer, and she gets assigned to the report. So she sees the error, and the symptoms suggest that something is going wrong at the expression level. So she asks Bob, hey, can you attach the expression log? And Bob is able to reproduce this issue on his computer, and he attaches the log. And then after looking at it, Alice sees that the variable's type wasn't resolved. So she asks, hey, can you attach the type log? But unfortunately, the type log doesn't explain why the type wasn't resolved. So at this point, Alice's best bet is asking Bob for the steps to recreate the bug on her machine and then debug LLDB and see what goes wrong. And we're lucky, and Bob he's able to share his binary and his debug information, and he attaches it all to the bug report, and he gives her steps how to reproduce. Great, right? Well, of course it doesn't reproduce on her machine. And something is different, like maybe it's the environment, maybe she's missing a file, or maybe your operating system is just behaving slightly differently. And unsurprisingly, this can lead to frustration for both parties. And it might even discourage Bob from filing a bug in the future. So reproducers are a way to automate this process. And the idea is to collect everything that we might need to reproduce with minimal or no interaction. And it greatly reduces the burden both on the reporter, Bob, and the resolver, Alice. And reproducers in LLDB were inspired on Clang. When the compiler crashes, you get a preprocessed source file and a command line invocation. And in LLDB, we'll need a little more things, but the idea is very much the same. So with reproducers, instead of going back and forth, Bob can attach the reproducer to the bug report, and then Alice can use it to replay and investigate the issue on her machine. So here's what our earlier example would look like with reproducers. And on the left-hand side, we see how to capture a reproducer on Bob's machine, and then on the right-hand side, we see how the reproducer can be replayed on Alice's machine. And until the reproducers are enabled by default, we need a way to instruct the driver to collect all the necessary information. And we do this with the -- capture flag. And then after the issue occurs, we type reproducer generate in the command interpreter. And the result is a folder that can be compressed and attached to a bug report. And then the session can be replayed by passing that reproducer to the -- replay flag. Also note that the reproducer is fully self-contained and that you don't have to specify the binary or any other command line flags as part of the replay invocation. So let's have a look at how reproducers work in LLDB. So before diving into the details, I want to take a step back and consider what reproducers are trying to achieve. And the goal is to reconstruct LLDB's state. However, the end result doesn't really tell us much. Assuming we have good logs and error reporting, we probably already have an idea of what went wrong. And what's more important here is why did it go wrong? And to figure that out, we want to debug LLDB while it's replaying the debug session. And as we've seen in the earlier example, there's two sides to reproducers. There's capture, where we collect all this information, and then there's replay, where we use that data to recreate the debug session. So for LLDB, we can identify two groups of data sources. There's information coming from the user, and there's information coming from the system. And a user can interact with the debugger either by typing commands or through the use of the public API. And then the debugger in turn will interact with the system, and this can range from reading object files with debug information to writing to the registers of the process being debugged. And one more important consideration in the reproducer design is minimizing its impact on the debugger's operation. Ideally, we want LLDB to behave the same way with reproducers as it would without. Because if the new functionality obscures a bug, or even worse, introduces a new one, we would be better off without it. And to achieve this, we reused as much existing infrastructure as possible, and we went to great lengths to make capture and replay either transparent or abstracted away. And as an added benefit, that tremendously helped during development to develop and test the individual components independently. So let's have a look at those components that we needed to touch for reproducers to work. And we'll start simple with the command line interpreter. And so everyone that has used LLDB, especially on the command line, has probably interacted with this at some point. So to reproduce commands entered by the user, it really suffices to just write them to file and then use this file instead of standard in during replay. And this is functionality that already existed. And there's a few details that complicate things, but overall, the idea is very straightforward. And that's it. So as mentioned, there's a second way to interact with the debugger. That's the public or SB API. And if you've ever wondered what SB stands for, here's your answer. It's scripting bridge. So LLDB exposes a stable C++ API, and it's accessible from Python, and it's what's used by IDEs such as Xcode, Eclipse, and Visual Studio Code. It contains everything you need to develop a tool on top of LLDB, and it's even what we use to implement our own command line driver. So here's an example of a simple Python script that uses the SB API to set a breakpoint and run a binary. It's extremely powerful, and it allows you to do a lot of fun stuff. So reproducing at the API layer means capturing and replaying API calls. And to do so, we need to know what function was called with what arguments. And sometimes we also need to capture the return value, but a little more details on that later. Also note that we don't need to capture every API call. If the implementation of one API calls another API, we do not want to record that. Consider this concrete example where create target is called from Python. And in the implementation of create target, we call get byte order in SB target. And we only want to record that create target call, because when it's replayed, get byte order will be replayed as part of its implementation. And capturing the latter would be redundant and even incorrect, because the function would be invoked twice, and that might have side effects. The API boundary is also dynamic. Depending on the situation, some function can be crossing the API boundary for one call, but not for another. For example, if we call get byte order directly from Python later on, we do need to record that call. And API boundaries are detected using a resource acquisition initialization type object consisting of two booleans. The static boolean is toggled whenever the API boundary is crossed. And when its value is true, we know that we are behind the API boundary. And the non-static boolean tracks whether or not the current instance of the object is the one that crossed the API boundary. And if both booleans are true, the call should be recorded and the static boolean should be unset on destruction. If only the static boolean is true, then we know we were called from behind the API boundary and should not record anything. All this logic is wrapped in a record macro that toggles the boundary and captures the function and its arguments. And the macro is inserted at the beginning of every API function. And currently, to give you some idea, we have over 2,000 instances of those macros in our implementation. And to record what function was called, we need a way to identify the function uniquely. And we do this by mapping the function's address to a monotonically increasing index. And this mapping is kept by a registry, and functions register themselves using these register macros. And although the function's address will be different every time we invoke LLDB, the order of these register calls will be guaranteed to be the same. And in addition to providing a unique identifier, the registry uses the function's signature to synthesize code that automatically deserializes its arguments. And all of this is done using templates, so as a consequence, these macros are type safe. When you do make a mistake in one of these macros, the synthesized function will fail to instantiate, and you'll get a nice error at compile time. Adding the register and report macros by hand would be tedious, time-consuming, and error-prone. So we built a utility called LLDB Inster on top of libtooling to automatically insert these macros. It uses the clang AST to construct the macros from the function signature and insert them in the right place. It also detects functions returning objects by reference, pointer, or value, and wraps them in a record result macro. And because macros are part of the code, we do not need to run this utility as part of the build process. You just run it once when you're extending the API. So now that we know how to capture functions, how do we capture the arguments? And fundamental types are really easy. Their value can simply be written to file. And this holds true for pointers or references to fundamental values as well, because if the value is later used, because if an API function uses a pointer to return, we can safely ignore it, because if that value is later used as the input argument to another function, we would just record it as a regular argument. Objects require a little more attention. None of LLDB's API classes are plain old data types, so we cannot just serialize their binary representation to file. Instead, we keep an index that maps an object's address. We keep a mapping that maps an object's address to an index. And because we capture return values for objects, we are guaranteed to see every object that crossed the API boundary. And then during replay, we can map these indices back to the actual address of the objects. So with functions and arguments serialized to file, replay is straightforward. We just read the function identifier and use that to find its signature in the registry. And that in turn is used to deserialize its arguments. And finally, we invoke it. And we repeat this as long as data is available. All right, so having covered user interaction, let's shift our focus on system interaction, starting with the file system. So even for our simple example, there's a bunch of different kinds of files involved. The most obvious one is, of course, the binary you're debugging, but there's also debug information, and this might come from object files, a DSIM bundle, DWO files. And then when you run the program, a bunch of shared libraries are loaded, and when you run an expression, we might have to recompile it. When you import a module, we might have to recompile it from the headers. And all of these files have to be part of the reproducer. So when replaying, the debugger should use the files from the reproducer and not the ones on disk. And the virtual file system transparently makes abstraction of where a file actually lives. And then the rest of LLDB can be completely oblivious to the file's actual location. And the VFS uses a YAML file that consists of a mapping between virtual and real paths. And the virtual file system was developed as part of Clang, and we moved it into LLVM so we could reuse it in LLDB. And as a result, it also uses LLVM's abstraction for manipulating files through memory buffers. And this posed an issue in LLDB where file pointers and file descriptors are commonly used. And there was quite a bit of discussion with the community on how to make it possible to devirtualize files, to make that possible, especially in regards with the API. And in the end, we found a solution that worked for everyone, and it involved moving some code into the VFS header and doing casts on the LLDB side. The file system class in LLDB serves as a wrapper around the virtual file system. All file system access has to go through this in order to work with the reproducers. It's also home to the file collector, which keeps track of every file that might be needed by LLDB. And when a reproducer is generated, it will copy all these files into the root and emit the YAML mapping that I mentioned before. And the file collector also integrates seamlessly with Clang, so we are informed of files used by the Clang compiler as well. So finally, the lowest level component that affected reproducers is the GDB Remote Protocol. And the GDB Remote Protocol is a simple serial protocol, and it's used to start and stop the debug process, as well as read and write its memory and registers. And it was originally designed as a remote debugging, for remote debugging, and it's widely supported on embedded devices. And because LLDB would have to support it anyway, we also use it for local debugging. And LLDB employs it to talk to the debug server, and depending on the situation, the debug server will either run locally on the host on your device or remotely on the device you're debugging. And so the GDB Remote Protocol packets provide a clean boundary between the debugger and the process you're debugging. And by capturing and replaying the packets, we can deterministically mimic the behavior of the debug process during replay. And this saves us from having to come up with a reliable way to relaunch the process and control it. And so when we create a reproducer, all we need to do is log these requests and replies to file. And then during replay, instead of connecting to the real debug server, we spawn a replay server that responds to every request with the next recorded reply. And because all user interaction is being replayed, the order of requests will be the same. And what's really great about this approach is that it's completely transparent to the rest of LLDB, which just thinks it's talking to a real debug server. And as an added advantage, this also allows us to reproduce remote debug sessions. So as of now, reproducers are still under development. So let's talk about some of its limitations and things we are currently working on. So some of LLDB's APIs take function pointers as an argument, which is something that is currently not supported. We could probably make things work if the past callback is another API function, but if the user defines its own callback, there's really no way for us to know to capture this. Void and data pointers pose another problem, and consider this example where a buffer is passed together with its length. Because of the way that we currently serialize arguments, there's no way for us to read the length before reading the whole buffer. And this is something that we can solve by having custom serialization for these kinds of functions, which are not that many. Another thing, today the lifetime of API objects is not tracked. So if an object is destroyed and another object ends up at the same address, we would serialize the wrong index. And for the same reason, during replay, objects are never deallocated. And we could solve this by adding some code to the object's destructor that informs the mapping that from now on, another object at that address will be a different one. Also, Swift was one of the main, or is one of the main drivers for reproducers, as it has proven to be particularly tricky to reproduce. And because reproducers are developed from the bottom up, this was like really the last stage in the development process, because Swift, for example, relies on clang. And for reproducers to work with Swift, we have to ensure that it uses the virtual file system so that all the files it uses are coming from the reproducer. And we have to ensure that we have the same kind of callbacks as Clang does so that our file collector is informed of any files that the Swift compiler might need. When it comes to files, LLDB currently includes everything that it potentially needs, and there's no differentiation based on where the file came from or what it's used for. And these files can be large, and there can be many of them. Probably we don't need all of them for reproducing. For example, it would be reasonable to expect system libraries to not affect or not cause a regression in the debugger. So we could choose not to include them by default. And even if we do need them, we can make that an opt-in feature. And this is really important because overly large reproducers would hurt usability. And we're working hard on finding a way to be more selective and prune down the amount of files included. When a reproducer is generated from the command line, as we saw in the earlier example, we have little constraints to the amount of work we can do. When the debugger crashes, however, we don't have any guarantees. For example, copying over all these files in a signal handler is not something we want to do. Clang sidesteps this issue by writing out its mapping and then re-invoking itself and copying the files over then. And this is something that we could do in LLDB as well. And one more important consideration is also the impact of reproducers on privacy. The reproducers can potentially include a lot of sensitive information, and it's imperative for our users to know exactly what information they would be sharing. And currently we print a generic warning about asking a user to look at the content of the reproducer directory. And this is also part why we don't gzip it or tar it yet. We want users to have a look at it. And this could be improved by being more specific, but without being too overwhelming, because we include so many files. So please try it out. If you encounter a bug in LLDB, please consider generating a reproducer and attaching it to a bug report on bugs.llvm.org. Finally, I want to thank everyone that's helped with this feature. I'm incredibly grateful for the feedback I got in code reviews, on the mailing list, and on IRC. With that, are there any questions?
So any question?
So I see you're using the virtual file system to record everything, and we try to do something similar to reproduce some stuff, and we had some issues when we try to record something on one OS and to replay it on another OS because the virtual file system is not really taking this kind of stuff into account. So is this also a limitation you have, or?
This is definitely a limitation that we have, and we don't intend to try to reproduce a bug on one operating system on another operating system, because things are so different. We have a lot of operating specific code that it wouldn't really make sense. For example, the packets that we would send to the GDB remote server would be very different on a Linux system versus on a macOS system. So we didn't run into that yet.
Okay, and another question, totally different. You said that you were recording what was sent to the debugger.
Yes.
But not when it's sent. Are there some situation when the timing of these commands could have some impact?
The GDB Remote Protocol is it's not stateless, but it's very simple. It's request reply. And if there's any non-determinism on the side of the process you're debugging, that doesn't matter because the packets are going to be the same. If we have non-determinism in the debugger, however, that could be an issue. But so far, that hasn't caused an issue. Thank you.
Any more questions? Okay, no question.
All right, thank you.
Thank you.